A different use of the chi-square distribution is the test for independence, which happens when we analyze categorical data, and we often wonder whether the variables, which will be qualitative, are dependent, whether they are independent. And the normality assumptions are not required for this problem. It's sort of, again, a non-parametric type of test. Which is sort of similar to the test for correlation, but it is for categorical data. The correlation is for quantitative data, numerical data, while this one is for counts or categorical data. The conservative hypothesis is to assume that there is no relationship or independence. Why should we assume that the two variables are related or dependent to each other? This is exactly similar to the assumption rho equals 0 in correlation. We are assuming that there is no linear relationship. Here we are assuming that there is no relationship between the two things. As in the test for goodness of fit, there is that the alternative hypothesis is not a choice of three hypotheses. So the alternative hypothesis is basically not the null hypothesis. So there is some sort of relationship, or one variable is dependent upon the other. Often the data, which are counts, are arranged in a contingency table, which we have seen in the previous clip, consisting of observed values O that are given to you. And the table, for instance, in here I have an example of a table containing 2 rows and 3 columns. And each cell is C11, C12, C13. So the first index represents the row and the second index represents the column. So this will be C21, meaning row 2, column 1. And this will be C23. And the test statistic is identical to the one for the goodness of fit. So it's the sum for all cells of the squared deviations between the observed and the expected value divided by the corresponding expected value. And we need to calculate the expected values, and we'll see how in just a moment. This test is performed at degrees of freedom which are equal to the product between the number of rows subtract 1 and the number of columns subtract 1. Like the test for goodness of fit, this test is always right-tailed because high values of the test statistic indicate discrepancies between the observed and the expected values, and so favor the rejection of the null hypothesis of independence. So we reject the null hypothesis every time the calculation value is higher than the critical value. So every time it falls in this region, which is always to the right side. So every time we have a test where the alternative hypothesis is not a choice of 3, but is simply the negation of the null, these tests tend to be right-tailed always. Computing the expected values for each cell, if we assume the null hypothesis true, then we are assuming that our events are independent, and so the probability that an observation falls in a certain row I and end, multiplication rule in column Y, we have to use the rule for independent events. So it's the product that it falls in row I times the product that it falls in column Y. Now, the P stands for probability. So probability that falls in row I is a number of favorables, so the row total divided the number of possible, so N, multiplied by same thing for falling in column I, J. It's the probability is the number of favorables is the total the column total divided by n. And because the expected values are equal to n times p, when I multiply n times my probability, I'll get n times row total divided by n, and the n will simplify, times column total divided by n. And so in the end, the formula for E is row total times column total divided by n. And so in this way we can calculate all the expected values. The only thing we want is that they are greater or equal than 5, because if we have the small expected value, then the difference O minus E squared tends to grow out of proportion, and therefore this is not reliable. In this case, if the E's are less than 5, we need to collapse the table by combining maybe 2 rows or 2 columns. The only exceptions that we have is when the contingency table is a 2 by 2, so 2 rows and 2 columns, then the test statistic should be replaced by the chi-squared corrected, which is still has the general shape, but the expected value is at the bottom. There is the square of the differences between observed by expected, but we take these differences in absolute value and we subtract 1/2 or 0.5 before squaring them, and then every other step is the same. We'll follow up with an example. Thanks for listening.